Okay, so we're going to continue looking at nomenclature. Continue looking at, we have done functional groups, and but we hadn't done the alkyl groups. So we looked at we talked about this last time. If I look at an organic compound, so I've got R, C double bond OH, this part of the molecule is the functional group, whereas this part of the molecule is the organic variable, right, which we call the alkyl group. And so while this suggests that compounds of this formula will have to be the same class of compounds, the same family of compounds. So all of these are going to have some elevated melting point, elevated boiling point. When they're solid, they'll all be crystalline. They will all have a pungent smell. They will all react vigorously with electropositive metals like sodium, magnesium, and so on, and evolve hydrogen gas. All of that is true because of the presence of the carboxylic acid functional group. But the R group can vary. And we spent a lot of time last day looking at the different functional groups. So the halogen, the alcohol, the thiol, amides, amines, carboxylic acids, blah, blah, blah. But what we're going to do today is look at the R groups, right, the so-called alkyl groups. And the way we get an alkyl group is from the corresponding alkane. So if you recall, alkanes have the generic formula CnH2n plus 2. And we get the alkyl group by basically taking off an H, so they become CnH2n plus 1. So what I'll do is look at the value of N, and N would start off at the value of 1. So for example, if I have N is equal to 1, 3, 4, 5, 6. If N is equal to 1, then this is going to be what's called methane. And the formula will be CH4. So C1, H2 times 1 is 2 plus 2 is 4. When N is 2, it's called ethane. And that's C2H6. Right? 2 times, so Cn is 2. 2 times 2 is 4, 2 is 6. When N is 3, it's called propane. And that's C3H8. And then butane, C4H10. Pentane, C5H12. Hexane, C6H14. And what you'll notice is a couple of things. Up until we get to C5, the names really are not particularly systematic, right? But when I get to 5, pent is the accepted prefix from the Latin for 5. Hex is the accepted prefix for 6. Hept is for 7, right? So if I have this would be this would be heptane, which is C7H16, and so on, right? So for carbon 1, 2, 3, and 4, the prefixes, the prefaces are meth, eth, prop, and bute. And unfortunately, that's not particularly systematic. But it gets very systematic at C5. So it's pent, hex, hept, oct, non, dec, undec, dodec, and so on, which we look at in a second. But also, because these are all alkanes, the name ends in ane. This part of it is a constant, right? And all that changes is the prefix. So the prefix indicates the carbon number, right? The prefix indicates the number of carbons in the compound in a simplistic way. So for C1, right, my prefix is meth, C2 is F, prop is C3, but is C4, and so on. Well, what about the groups, right? So in other words, the way we get the alkyl group is we remove the ANE and replace it by YL, so alkane gives rise to alkyl, and essentially we're just putting off an H. What does that mean? So this, for example, is methane. Okay? Well, I could have this organic compound, right, which is an alcohol. I could have this organic compound, which is an amine. And essentially all I did is I'm replacing the H of methane by some functional group. But that leaves behind the CH3 unit. Right? So this is my organic compound, right? This is my alkyl group, and that's my functional group. Alkyl group and functional group. So the way we name the alkyl group is from the prefix, right? It's from the alkane. So if I have this compound, this is ethane, but maybe that's going to give rise to let's say this compound. Right, so this is my functional group, that's the thiol, and this is my alkyl group. So I can get the alkyl group, which is C2H5 from C2H6, right? So I replace an H by whatever my functional group is. So that's my functional group, and this is my alkyl group. So we get the alkyl group by removing an H from the alkane. And the name of the alkyl group then takes essentially the prefix from the same number of carbons. So this is methyl. So from methane, I get methyl. And methyl is abbreviated as uppercase M, lowercase e. If I have ethane, that will give rise to the ethyl group. So I replace the ANE by YL. And that's abbreviated uppercase E, lowercase t. So the first letter is capitalized, it's uppercase. The second letter is lowercase. Propane gives rise to propyl, which is PR. Butane gives rise to butyl, which is uppercase B, lowercase u. Pentane gives rise to pentyl, right, which is PE. Hexane gives rise to hexyl, which is HE. Heptane, there's already so heptane gives rise to heptyl. There's already HE, so it's often written as HP for heptyl and so on. So it means then, for example, I could write this compound. I can write, let's say this compound, let's say the alcohol. I can write this as CH3OH, as I've drawn it out here in the dash structure. Or I can write CH3OH. Or I can write MEOH. All of these are equivalent depictions of the same compound, right? So all of these represent methanol. Right? So all of these are equivalent depictions of methanol. Okay? And then in a similar fashion, instead of writing it like this, I could write this compound as C2H, well, I can write it in two ways. I can write this as either CH3CH2SH or C2H5SH or ETSH. All of those are equivalent depictions of ethane thiol. Right? So I can write out the sort of dash structure, and I didn't have the dash for SH. Or I can write it as the methyl and the methylene, right? So the CH3 and the CH2. Or I can condense these further into the condensed structure, which is C2H5. That's the ethyl group, which is ETSH. So what are the prefixes for which you're responsible? Well, it's meth, eth, prop, but, pent, hex, hept. As you might expect, C8 is going to be oct, then which is OC. C9 would be non, which is NO. C10 is dec, which is DE. C11 is undec, and C12 is dodec. Okay? So you're responsible for the names of the first 12 prefixes, from C1 to C12. So meth, eth, prop, but, pent, hex, hept, oct, non, dec, undec means 1 plus 10, dodec, 2 plus 10. So you're responsible then for the prefixes for the first 12 of the alkyl groups. All right. So now we know all of the common prefixes that we're responsible for. We know all of the functional groups. We're going to pull that together and try to name organic compounds. Now, let me just say, so for example, in this case, you will see in textbooks, really all 4 of these iterations for the same compound. And you must be able to move seamlessly between one and the other, right? So all of these are equivalent depictions of the same compound. And you must be, savvy enough to flip between them. Or if I draw the bond line structure, it's going to look like that. Right? So all of those are equivalent depictions of the same compound. All right, so what we want to do now is try to name organic compounds. And there are a set of rules that govern nomenclature, which is the system for naming organic compounds, well, naming compounds in general. I will say that the system we use is the IUPAC. It's the IUPAC system, which is from the International Union of Pure and Applied Chemistry. So IUPAC is a governing board for chemistry, and they're charged with maintaining certain protocols, one of which is a naming system for organic compounds and inorganic compounds, macromolecular systems, etc., etc., etc. So what we're going to do then is look at the rules for naming organic compounds. And I'm just going to, you could list a series of rules, which any textbook you have will go through the list. And I invite you to do that, but I'm just going to jump in and start naming things. To me, it's just better with practice. So let's go ahead and try to name that compound. Well, the first thing we're going to do is we're going to ask, what class of compound is it? Is it an alkane, an alkene? Is it an alcohol? Blah, 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 blah. So I look at it, and I'm trying to figure out what is my functional group. Well, all I have here are carbon-carbon single bonds and carbon-hydrogen bonds, which of course are single bonds. That means this compound is an alkane. So I'm going to write ANE. I'm going to write what we call the base name, ANE, right? And when we name organic compounds, it's sort of bass backwards. We name the base name first. So it's ANE for A, because it's an alkane. Then I'm going to ask, how long is my longest chain? And my longest chain, basically, I'm going to sort of mentally take my finger and move it along the carbon chain even if it means I have to bend a corner, right? I'm going to move it on the carbon chain and try to find the longest continuous chain that I don't have to lift my finger for. So if I go 1, 2, 3, 4, 5, right? That's got 5 carbons. My prefix for 5 is pent. So I'm going to call it compound pentane. And we're done. What if I had this compound? Okay. Well, if I look at it, that compound still has 1, 2, 3, 4, 5. So, well, it's still an alkane. It's only got carbon-carbon single bonds and carbon-hydrogen bonds. So it's still an ane. But now, if I look for my longest chain, it's not the 1, 2, 3, 4, 5. It's now 1, 2, 3, 4, 5, 6. Or, if I started from here, 1, 2, 3, 4, 5, 6, or 1, 2, 3, 4, 5, 6. So my longest chain, I'm going to pick mentally, my longest chain doesn't matter how I do it, I'm going to take this as my longest chain. And that longest chain has 6 carbons in it, so that is a hexane. But it's not just hexane, it's got that thing hanging off it. It's a substituent, right? So it's a hexane that has an ethyl substituent. This is C2H5, a C2 is ethyl substituent. So essentially then this compound is an ethyl cyclohexane. So I have my major functional group, in this case it's an alkane, the length of the longest carbon chain, and I have the substituent on the chain. But the problem is, that substituent, I need to indicate where on the chain that substituent is. So I need a number that identifies where on the carbon backbone that substituent lies. That number is called a locant. Right? That number is called a locant. So I need to have a locant that indicates where on the backbone of the hexane does my ethyl group lie. So what I do is, I'm going to number the chain, starting from either end, and try to find the lower number for the locant. So if I number from here, this would be carbon 1, 2, 3, 4, 5, 6. Right? That would suggest it's going to be 3 ethyl heptane. If I number from here, it's going to be 1, 2, 3, 4, right? 5, 6. And that will be 4 ethyl heptane. I want the substituent, the ethyl substituent, to have the lower possible locant. So I'm going to say this compound is called 3 ethyl hexane. Now notice, we separate the substituent from its locant by a hyphen. So this is 3 ethyl heptane, 3 hyphen ethyl heptane. We join the name of the last substituent, you see there are cases where there are more, to the base name. So if I'm writing cursive, I will combine the L with the H, right? But if you're just writing, non-cursive, you have just 3 ethyl hexane, there'll be no space between the ethyl and the hexane. So the IUPAC name for this compound would be 3 ethyl hexane. What if I had this compound? What if I had to name that compound? Well, again, this compound is an alkane, only carbon-carbon single bonds and carbon-hydrogen bonds. So this is going to be an alkane. That's what I write first. What I want now is the longest carbon chain. And I can go, let's see, 1, 2, 3, 4, 5. Or 1, 2, 3, 4, 5. So either way, right, it's going to be 5 carbons in the longest chain. So I'm going to, or I could go 1, 2, 3, yeah. I could also go 1, 2, 3, 4, 5. But the reason I'm going to pick one of these, let's say I'm going to go here. Right? I'm going to pick that as my longest chain. Is because when I have a choice of equal chain lengths, because I could have said this is 1, 2, 3, 4, 5. I could have gone with the green. If I pick the green one, I only have one substituent. If I pick the red one, I'll now have 1, 2, 3 substituents. So I pick the longest, so I want to pick the longest carbon chain. But when I have two different options for the longest chain, I want to pick the chain that is the most highly substituted, or that is more highly substituted. There are more things coming off of it. So if I pick the green one, right, which is also 5, 1, 2, 3, 4, 1, 2, 3, 4, 5, then I'll only end up with a single substituent, this thing, on the chain. If I pick the red one, whether it's this red one or that red one doesn't actually matter, because of the same result. I'm going to have 1, 2, 3 things hanging off of it, right? Okay, so I'm going to pick the red one. So just for the sake of clarity, I'm going to take off the green, so I'm not going to confuse myself. Okay, so it's aim. I picked this as my longest chain, and that has, what was it, 5, 1, 2, 3, 4, 5 carbons. So this is pentane. It's not just pentane, it's got 3 substituents. It's got methyl groups, right, and an ethyl group. Well, so how do I arrange those? Well, we do it by alphabetization. So ethyl begins with E, methyl begins with M. So E precedes M in the alphabet. So I'm going to call this ethyl methyl. But if you look, there's not just one ethyl group. There are two. There's not just one methyl group. There are 2 methyl groups. So I don't say methyl-methyl. What I'm going to say is dimethyl. So the question is, the D now complicates things. So D precedes E in the alphabet. So do I say it's dimethyl ethyl, right? Or ethyl dimethyl? And the answer is, when we are dealing with the number of substituents, so di, tri, tetra, blah, 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 we don't use the prefix of the term that indicates quantity. So although D precedes E in the alphabet, the D doesn't matter, because that number indicates this letter indicates the number of those groups. That doesn't count in the alphabetization. Okay? So E would precede M, and I will call this compound an ethyl dimethyl pentane. But it's one of many ethyl dimethyl pentanes. I need to indicate where those groups are by locus, so I can distinguish my ethyl dimethyl pentane from all the other ethyl dimethyl pentanes. So I want to get locus. If I number from left to right, I guess, so if I number from left to right, then this will be carbon 1, this will be carbon 2, and each methyl needs its own locant, even though the 2 locants are the same. So each substituent must have its own locant. So this will be carbon 1, methyls, so there's 1 at carbon 2, another carbon 2, and then my ethyl will be at carbon number 3. So the sum of those is going to be 7. If I numbered from right to left, going this way, then this will be carbon 1, 2, 3 for my ethyl, 4, 4 for the 2 methyls. That's going to give me 8, that's going to give me 11. 7 is the smallest sum of the locants. So we're going to number left to right. And I'll call this compound 3 ethyl 2 dimethyl pentane. Okay, a couple of things to watch here. I'm going to separate the substituent from the locant by hyphen. Substituent from the locant by hyphen. I'm going to separate information about a particular substituent. All of this is information about the ethyl. From the information about another substituent, right, all of this is information about the methyls. I'm going to separate those 2 packets of information by hyphen. So hyphens are used to separate locant from substituent, and information about a given substituent from information about another substituent. To separate locants referring to the same substituent, in other words, the 2 methyls, I'm going to use a comma. So this is 3 ethyl, or 3 hyphen ethyl, hyphen 2, comma 2, hyphen dimethyl pentane. Or 3 ethyl 2 dimethyl pentane. Right. So in addition to the di, tri, tetra, penta, blah 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 blah, the prefixes that indicate the quantity of the substituent. There are two other descriptors, if you will, that are not featured in alphabetization, which we'll get to in a second. It's the sec and tert, which we talk about in a minute. So those do not feature in alphabetization. In fact, let me just talk about those now. So if I look at say C4H9Br, it turns out there are 4 different versions of that compound, right? Well, I should phrase that. There are 4 isomers with that formula. There is this one. There is this one. And how am I doing this? I'm going to put all 4 carbons in a line and then move the bromine from carbon 1 to carbon 2. So those are 2 different compounds. Now, if I move it from carbon 2 to carbon 3, that's the same as this one. If I put it on carbon 4, that's the same as that one. So these are the only 2 isomers I can get with all 4 carbons in a straight line, right? So linearly. Well, I can now have 3 carbons in a line, right? And then I can have the 4th carbon here, in which case I have 2 options. Put the bromine on the primary carbon, either here, here, or here, it'll be the same thing, or put the bromine on the tertiary carbon. And those are my 4 options. Well, this one is often called N-butyl, or normal butyl. This one is called sec-butyl, or sometimes S-butyl. This is called isobutyl, or I-butyl. And this one is called tert-butyl, or T-butyl. So, if you notice, the sec and the tert have hyphens. The iso does not. So we would use the iso as part of we use the I in iso as part of the nomenclature. So it would feature in alphabetization. The sec and the tert don't. Okay? Although, if you had both a sec and a tert in the molecule, then you would put S before the T. Okay? Just a quick point about this. This is called normal butyl. This is called sec butyl because the bromine, or the substituent, is on the secondary carbon. That's the same reason this one is called a tert butyl, because the substituent is on the tertiary carbon. Iso is something you will see quite often in organic. In fact, you will also see tert quite often. The iso unit is one that has what's called a geminal dimethyl. It has a geminal, or gem, dimethyl. In other words, it's a species that has two CH3 groups on a given carbon. Right? So here's my carbon that has two methyls and an H. Right? So that's called the iso function. The same thing is true, by the way, for propyls. If I have C3, H7OH, I have a couple isomers of that. I can have this one, and I can have this one. This is called N-propyl alcohol. This one is called isopropyl alcohol. So this is my iso group, right? It's got a gem dimethyl unit. So it's got a carbon with two CH3s on it and an H. Right? So that's the iso function. Okay, so sec and tert don't feature in alphabetization. Incidentally, the first time you start seeing isomerism with organics is with C3. You don't see it with C1, obviously, or C2, obviously. But the first time you have freedom to sort of move a functional group with consequence is at carbon number 3. And the number of isomers will increase with the number of carbons. So with carbon number 3, you only have 2 isomers if you want to have the OH. With carbon, with a C4 species, you now have 4 isomers. And that number gets bigger and bigger and bigger as the number of carbons increases. Okay. What if I had, what if I had something like this?